we get to part of the semester where we take what we learn from the sample, account for variability, and make inference about the population we were trying to say something about to begin with. So we're going to suppose that we use the sample mean, y bar, or x bar, as our best guess of the population mean mu. That would make sense. If I was trying to estimate the average weight of all Carolina students, mu, then I could, for instance, get a sample, hopefully a random sample that's unbiased, of 100 Carolina students, and I could get them into the Thompson Student Health Center and I could weigh each of them. And what would I do to get an estimate of the average weight of all Carolina students? I could use the average weight of my sample as a good first guess about what the average weight of all Carolina students is. So we're going to assume that our sample mean, the average weight of our 100 students, is close to the target, is close to the true average weight of all Carolina students. But we know it's not going to be exactly on the target every time. It's also understandable, we all can envision that if we were to take another sample from the same population and calculate the sample mean for that sample, it would also not be exactly equal to the population mean, that is the average weight of all Carolina students, and it's also going to be slightly different from the average weight of our first sample. Now we're going to formally define this notion that we've been talking about all semester so far. The fact that a statistic is going to vary from sample to sample, or the fact that each sample looks a little bit different from every other sample from the same population, is called sampling variability. Now, the statistics then that we calculate on those samples are also going to be a little bit different from each other. Hopefully most of our statistics, most of our sample means, if we were to get many, many samples, will be really close to the population mean. But we know that sometimes we're going to get a sample mean that's estimating the population mean a little bit too high, and sometimes we're going to get a sample mean that's estimating the population mean a little bit too low. So if we describe the center of that distribution and how often those sample means are a little bit too high and how often they're a little bit too low, we can picture a histogram where we could graph all the resulting sample means. That distribution, if we describe its shape, center, and spread, is called the sampling distribution of the statistic. We're going to study the sampling distribution of the sample mean y bar, or x bar, whatever you want to call it, but right now we're calling it y bar. Now this boxed set of theorems is going to be extremely important for the rest of the semester. We will remind you of it a lot. So let's pay close attention to what is in this box. If I'm thinking about that sampling distribution of the sample mean, y bar, we have three facts that you need to know. The first one is that the mean of the distribution of all the y bars, that is the population mean, if I were to take many, many samples, so let's suppose I have one sample of 100 USC students and I calculate the sample mean weight, let's say it's 150 pounds. Then I get another sample of 100 USC students, and let's say the average weight of that sample is 155 pounds. My next sample of 100, my average weight is 160 pounds, etc. If I think about taking many, many, many samples of 100 USC students and calculating the sample mean weight of each one, that's going to describe a distribution, can be described by a distribution. Well, there is some true population mean of all those possible sample means. That is what this mu sub y bar is indicating. So the average sample mean across all the possible samples from that population is the population mean of the original y that we started with. That is the mean of the distribution of all the sample means is equal to the mean of the distribution of just the random variable y, the weight of a USC student that we started with. Now the second fact is, so we know where those sample means are centered. The standard deviation of that distribution of all possible sample means is the standard deviation sigma that we started with. That is the standard deviation of just the random variable y divided by the square root of n. Now let's take a minute and try to digest these two facts. So let's use the concrete example again. Imagine that we've got a sample of 100 USC students, and let's suppose that the true average weight of a USC student is, if we could weigh all USC students, let's just make up a number and say that the average weight, if we were to weigh all USC students, is 150 pounds. So mu would be 150 pounds. One sample mean, if we took 100 students, might be 150 pounds. The next one might be 155. The next sample could result in an average weight of 160 pounds. They would vary. So what the first fact is saying is that if the true population mean, the true average weight of all USC students is 150 pounds, then our sample means are going to also be centered around 150 pounds. And how much do they vary? How much do those sample means vary? Well, let's suppose the original variability, sigma, was 10 pounds. Let's use a whole number. So if I took individuals from this population, the first one might weigh 160 pounds, the next one might weigh 180 pounds, the next one might weigh 140 pounds. Those weights would vary quite a bit. However, if I took a sample of 100 USC students, my first average weight might be 155 pounds, my second average weight might be 140 pounds. You can imagine that if I'm averaging together 100 people, that sample mean would vary less from sample to sample. And now picture if I had a sample of 1,000 USC students. The chances of me getting a really, really big football player and a really, really small cheerleader, they're going to balance each other out more when we have a larger sample. So the sample means are going to vary less if we have a bigger sample size. And that's why the standard deviation of the distribution of y bars is smaller than the standard deviation of the original variable that we started with. By how much? You cut it by a factor of the square root of n. All right. So we've talked about the center of the distribution of all possible sample means from a population, and we've talked about how much they vary from sample to sample. That is by sigma divided by the square root of n. And now we need to talk about the shape. So we have two things here. The first one is, if your y's came from a normal distribution, then the shape of the distribution of the sample means is also a normal distribution. However, if your original variable was sampled from a distribution that was not normal, then we can use the central limit theorem. And the central limit theorem says, as the sample size grows large, the distribution of the sample means still becomes approximately normal. So let's investigate this central limit theorem with some pictures. So notice that we said with a large enough sample size, the sample mean ends up having a normal distribution. But how large does it need to be? Well, it ends up being, it depends on how far from normal you start with. We'll talk about this a lot. So here's a picture from the third edition of the text. We have a distribution that's trimodal. So when we smoothed the histogram, we had 3 bumps in it. And when we had samples of size 16, the sample means end up having that distribution. When we have sample sizes of 32, it smooths out a little bit, the distribution of all possible sample means. When we have samples of size 64, it's really getting close to being a normal distribution. And samples of size 128, it's pretty much a symmetric bell shape. In the next example, we have y denoting the number of eye facets in a fruit fly. Now, if you're counting something, that's not a continuous random variable, that's discrete, so certainly it's not going to be normally distributed. distributed. So we don't even start with anything that can be a normal distribution. But here, because the original distribution of eye facets, when we smooth the histogram, looks fairly unimodal and symmetric, by a sample of size 16 is looking really like a normal distribution, and by a sample of size 32, it's almost certainly a normal distribution. Now, what are we going to do with this new information when we make calculations? Well, let's do an example right now. So from example 5.2.4 from your text, let y denote the weight of seeds, where y is distributed as a normal distribution with a mean of 500 and a standard deviation sigma of 120. We want to find the probability that y bar, that is the sample mean of 25 observations, is larger than 550. So what are we going to do to find this? Well, because our y's started out as a normal distribution, we know that the sample mean also has a normal distribution from our boxed set of theorems. So since y is distributed as a normal, then y bar is also distributed as a normal random variable. Now that we know we have a normal distribution, we can make our calculation. So, we want to find the probability that the sample mean of observations is larger than 550. And since we know the sample mean has a normal distribution, since the original y's also had a normal distribution, I can draw a picture of the distribution of sample means. Now we know that the mean of this normal distribution, that is the mean of the distribution of all possible sample means, is the mean of the original distribution. So that's going to be 500. That was given up here in the problem. However, our standard deviation of the distribution for y bar is not just sigma anymore. It's the original sigma divided by the square root of n. That's from our box theorem, since we're dealing with the distribution of the sample means rather than just individual observations. And so sigma from my blurb is 120, and n is 25. So I can draw my picture. I want to find the probability the sample mean is larger than 550. And so that's going to be 1 minus, because we want the area to the right of a number in a normal distribution. So 1 minus p norm, 1 minus the area to the left of 550 in a distribution that's centered at 500 with a standard deviation of 120 divided by the square root of 25. And we can go to R and calculate that. So 1 minus P norm of 550 with a distribution centered at 500 and a standard deviation of 120 divided by the square root of 25, and I get 0.019. All right, 0.019. Very good. Let's do one more example. So this is taken from your textbook. Serum cholesterol levels in a population of 17-year-olds follow a normal distribution with a mean of 176 milligrams per deciliter and a standard deviation of 30 milligrams per deciliter. So notice that we're saying our variable, serum cholesterol levels, have a normal distribution. So we're going to use that in a little bit. Find the probability a randomly selected 17-year-old from this population has a serum cholesterol between 166 and 186 milligrams per deciliter. So this is just for one randomly selected 17-year-old. So that is, we want the probability that Y is between 166 and 186 milligrams per deciliter. We're told that Y has a normal distribution, so we can simply draw a picture of our normal distribution. It's centered at 176, and the standard deviation is 30. We want the probability of being between 166 and 186, so we want the area in between those two values. So that is P norm of 186, so that's everything to the left of 186, in a distribution centered at 176 with a standard deviation of 30, minus everything to the left of 166. P norm of 166, centered at 176, standard deviation of 30. And I can punch that in R. So I want P norm of 186, centered at 176, standard deviation of 30, minus P norm 166, centered at 176, standard deviation of 30, and I get 0.261. So that one's 0.261. Suppose we want to find the probability the sample mean cholesterol for a random sample of 9 17-year-olds from this distribution will be between 166 and 186 milligrams per deciliter. So notice that our probability, we want to find the probability the sample mean of 9 observations is between 166 and 186. Now we need to know what distribution the sample mean has. But from our boxed theorems, we know that since the serum cholesterol is normally distributed, so is the sample mean of observations from that normal distribution. So we can draw a picture of our normal distribution for the sample mean of observations. We know that it's centered at the original mean of 176. However, since we're looking at the distribution of the sample means, the sigma is going to be the original sigma, 30, divided by the square root of the sample size. So there are 9 17-year-olds, so we're taking the square root of 9. And so we have our mean and our standard deviation of our normal distribution. We want to find the probability of being between 166 and 186 in this normal distribution. And that's going to be P norm of 186 in a distribution centered at 176 with a standard deviation of 30 divided by the square root of 9, minus everything to the left of 166, so P norm of 166 centered at 176, standard deviation of 30 divided by the square root of 9. And we can punch this in R. So it's the same statement as our last question, our last example, only we've got to put those divided by the square root of the sample size piece in. And we get 0.623. So 0.623. And it would make sense that our probability of a sample of 9 17-year-olds, the sample mean of a sample of 9 17-year-olds being clustered around the true mean would have a higher probability, 0.6, than just the probability of one single 17-year-old from our previous